again. Let's continue on in chapter 1. So in section 1.3, we're dealing with the classification of matter. So all of the matter that you see around you, how do you divide it into different categories? You have this type of matter, you have that type of matter, and that type of matter. How can we divide it up? A couple of ways the textbook talks about is one, the first method is by texture. So all matter is either a solid, a liquid, or a gas. The second method is more involved, and that's by composition. What substances is the matter composed of? Okay, what types of substances? Like, are we talking about water, gasoline? What are the components, the composition? So those are the two ways to classify matter that we'll discuss. So the first way is by texture. So let's jump over. I made my notes again. Okay. So the classification of matter. Well, first of all, let's define matter. Matter is anything that occupies space and has mass. It's almost everything that you see around you, except for possibly the light. For instance, this paper, the pen that I have, or the pencil that I have in my hand, the air that's surrounding us, all matter. So if you want to classify this by texture, there are three main types: solids, liquids, and gases. Now solids, the particles, you can see some solid chunk, some cube of something right here. The particles, whether they're atoms, molecules, or ions, are packed very closely together. So there's a lot of matter packed into a small space. So that means it's pretty heavy because there's lots of matter packed in there. So that means it's dense. We'll talk about density later on in this chapter, but solids are typically dense. They are also rigid. These particles are not flowing past one another. They're held fixed, and they occupy their positions and they don't move around. Remember, solid particles might vibrate around, but the particles don't flow past one another like liquids and gases do. So solids are rigid. They have a fixed shape. That's because the particles do not move around. They're also incompressible. We cannot really compress a solid into a smaller volume. You can try, it's really hard, and you pretty much can't do it. They have a fixed volume and a fixed shape. Now, solids can be divided into a couple of categories. Most solids are crystalline, meaning the particles have a nicely ordered structure. So you have the particles along straight lines, if you could see them, and then a next row of particles all in a line, and the next row all in the line. So a nice ordered arrangement in the particles, and a long range order if you're able to see the particles. So those are crystalline solids, crystals. Okay, amorphous solids are less common, but examples are glass and plastic. Amorphous solids, the particles do not really have a well-ordered arrangement. They're just sort of, frozen in whatever configuration they happen to be in, but no long-range order like crystals have. So sodium chloride is a crystal, and if you're able to see those particles, you would have the sodium cation, the chloride anion, then the sodium, the chloride, and they'd be all in a perfect line, and you go in the three dimensions perfectly this way and perfectly that way, nice, perfectly cubical, the particles 90 degrees in this way, and then another row 90 degrees in that way, so even right angles, so really high order in the particles for solid crystals like sodium chloride. Glass, it's just, the particles are frozen in place, no order. Okay, we'll come back to crystals later on in chapter 11, I believe, second semester. Okay, liquids are a different category. So liquids, the particles are also packed closely together, but this time they're able to slide past one another. Liquids flow. So there is a lot of mass in this small space. So liquids are also pretty heavy, they're pretty dense, but the particles this time can flow past one another. So liquids take the shape of their container. And they're also, since the particles are packed closely together, they're pretty much incompressible. So the shape might be able to change, but the volume is fixed volume, pretty much incompressible. Gases, on the other hand, the particles are very far apart. They're flying around independently of one another, so gases also flow. And also, since there's not a lot of particle, not a lot of matter in a given space, they're pretty light. They're not very dense. And since there is a lot of space between the particles, you can compress gases fairly easily. So they're compressible. Solids, liquids, and gases, the three main states or phases of matter. There is a fourth one called the plasma, and these are charged gases, and they behave a lot more different than regular non-charged gases do. So maybe we'll get to see plasmas in a couple places in Gen Chem, but we generally stick to solids, liquids, and gases. Now, these four states of matter are closely related to the four Greek elements: earth, water, air, and fire. In fact, there's a direct correlation between earth, water, and air and solid, liquid, and gas. Okay, earths were in general mostly solid materials. Liquids, in general, like anything that was water was something that just flowed like a liquid. Like mercury was considered to be mostly water back then. Anything that was, vapor, like smoke, that was called an air. And the reason there were the different types of earths look different from one another is because, although, like if you have a chunk of dirt, it would be mostly earth, but it'd have a little bit of water, air, and fire in there. But if you have another piece of earth, something like, a bush, well, it would be mostly earth, but it would have different proportions of the other ones in there. Most of the earths out there were, had a few of the others as impurities, and that's what explained all the different types of matter that we had around us. But still, there was a very close connection. Now, fire was a type of Greek element that instigated change among the other ones. For instance, if you added fire to some liquid, you would vaporize it and you would turn it into air. And today, we have a close connection between that and energy. Energy is what instigates change today. Now, we'll talk more about the Greek elements and the history that led up to the modern definition of elements in the next chapter. Okay, just a brief overview right now. So that's the first way to classify matter, which is by texture: solids, liquids, or gases. Now, the second, more detailed classification is by composition. What substances is the matter composed of? First, I want to detour into an historical note. Long ago, the philosophers believed that all matter is made of four basic elements: the earth, water, air, and fire. And the reason for the various types of matter is they contain different proportions of these four elements. We just explained that. A tree would have mostly earth and a little bit of water, air, and fire. And then a bush might have, mostly earth, and then maybe a little bit different proportions of the water, air, and fire. And that's what made those two, types of earths different. Okay. So, for example, Dry dirt contains mostly earth and very little of the others. Wet mud contains probably a lot of earth and a lot of water, but maybe little else. So that's another example. Now, through the centuries, people became very skilled at separating matter. So, the Bronze Age and the Iron Age, people were able to smelt ores, dig stuff out of the earth and produce material, from it. And they became experts at taking a chunk of matter, which is usually a mixture of different components, and separating it into its constituents. For example, someone who knew what they were doing could take some salt water and separate it into its salt and water constituents. So the salt water is a mixture, and then if you separate it into salt over here and water over there, well then these are two simpler substances. Okay? Now, eventually people were able to even take salt and separate it further into a metal type of material and a vapor. So sodium, metal, and chlorine gas. That, it took a while for people to figure out how to do this. I think the 1800s, okay, they figured out how to separate salt. And also water could be separated into hydrogen and oxygen. Okay, so these are even simpler substances than those two right there. Now, these last four substances cannot be divided any further, and today we call them elements. So no matter how hard you tried, you couldn't take sodium metal that you got through this process and take that and divide it into any other simpler components. So there's no other components that seem to make this up. Same thing with chlorine gas. This cannot be divided up into its components any further. Neither hydrogen nor oxygen. So eventually, someone said, "Hey, let's call these things the elements. Not earth, water, air, and fire. Let's call the things that we can't separate anymore. Let's call those guys the elements." Okay? That someone is Robert Boyle. He said that in the 1600s. He proposed a new definition of element, which was different than the old Greek elements. So an element, according to Robert Boyle, and which is our modern definition for the most part, it's a substance that cannot be further broken down into simpler substances by any chemical means. Okay, like by any laboratory technique, you cannot divide an element into anything more simple. Okay, it's not made of multiple components. It's the last component. It's the end of the line. Okay, now elements are rarely seen in nature. More common are compounds. So I'm giving you some definitions here. An element is a substance that cannot be further broken down into simpler substances. Well, you hardly see these in nature. In fact, the only source for pure metals way back in the day were like meteorites that came from the sky. Okay, that was the only way that you could get pure metal until people figured out how to smelt ores. More common is compounds. A compound is a substance composed of two or more elements combined together in fixed proportions. Okay, fixed proportions, very important. So, for instance, when we took this salt and this water and we separated it, this mixture, into salt and water, these are actually compounds. This compound is composed of sodium and chlorine, and it's in fixed proportions. Okay, And this compound, water, is composed of hydrogen and oxygen in fixed proportions. What I mean by fixed proportions, or what's meant, is that water, no matter where you get your water from, it's always 89% oxygen and 11% hydrogen. Okay? If you have 100 grams of water, 89 grams of it is the element oxygen, and 11 grams is the element hydrogen. It doesn't matter where your water comes from. It's always in that ratio, 89 to 11. Okay? 89 to 11. So, I can't remember what the ratio for salt is, but it's fixed. It's always that same percentage by mass. So that's what a compound is, composed of two or more elements combined in fixed proportions. Now, a mixture, which is like what we started with up here, salt water, that's a combination of two or more substances mixed together, but the proportions can vary from sample to sample. So the salt water that I make might be just have a little bit of salt and a lot of water, but the salt water that you make might have a lot more percentage of salt and as opposed to water. So depending on where you get your salt water from, it could be a different percentage of salt in there. So 100 grams of salt water that I make might only contain 1 gram of salt, but 100 grams of salt water that you make might contain 10 grams of salt. So the proportions can vary for mixtures, but not compounds. Compounds, it's always fixed. So here's an example of breaking down a mixture. Suppose this time we're starting with sugar water. So you see the blue water with the red sugar particles. We're talking about regular table sugar, which is sucrose. Okay? Now you can't really see the sugar particles. It looks just like water, but I just drew them in there so we can tell they're in. Okay, so this is sugar water. It's a mixture because it has variable proportion. Sugar water you get over here might contain lots of sugar, but sugar water you get over there might contain a little bit. So it depends on where you get your sugar water. That determines the proportions of sugar versus water. Now, mixtures do have a variable composition, as we just said. Now, this particular mixture is what's called a homogeneous mixture, meaning the components of the mixture, the sugar and the water, are mixed thoroughly and uniformly, all the way down to the smallest pieces. There are no clumps of sugar molecules in any one area. So all of the sugar molecules have become completely separated from each other, and they're completely dispersed and mixed evenly and uniform throughout the entire liquid. Even the little nooks and crannies all the way up in the corner, you have sugar molecules there, they're all evenly mixed. And if you were to take a teaspoon of the sugar water up here, and a little teaspoon, it should contain about the same amount of sugar as a little teaspoon of sugar water that you obtain down there. So evenly mixed, all right? There are no clumps of sugar anywhere, all right? Now, mixtures like this can be pretty easily separated into their constituent substances. Okay, you can separate sugar and water into the sucrose, sugar, and the water. And it doesn't require any crazy chemical reactions. Mixtures can be separated into their constituent substances by physical changes. All right. Now, physical changes are like boiling, evaporating. We're not changing the identity of any substances when we do physical changes. So the way you would separate sugar water is you would boil off the water, and you collect that somewhere else, and then you're left with the sugar residue inside of the container. So that would be one way to separate sugar water. So suppose you do separate it, and you have your sucrose sugar over here, and then your pure water over there. Now, these pure substances are compounds. Okay, water is a compound because It's composed of two or more elements in fixed proportions. Now, to break down water into its constituent elements requires a more vigorous process. It requires a chemical process. Okay, we actually have to change the identity of the substance. We're starting with water, and now we're getting hydrogen and oxygen afterwards. So it requires chemistry. All right, now this is a compound because it's composed of the same proportions of hydrogen to oxygen. You remember, water always has 89% oxygen and 11% hydrogen. Sucrose is also a compound and can be broken down into its constituent elements, which is carbon, oxygen, and hydrogen. Let me see what the percent composition of sucrose is. Sucrose percent composition. Just Googling this up here. Sucrose percent composition. Let's see. It looks like it's hydrogen 6%, carbon 42, oxygen 51. 6, 42, 51. Okay, so no matter where your sucrose comes from, 6% hydrogen, 42% carbon, and 51% oxygen. Okay, that's the percentages of sucrose, fixed percentage, right? So carbon, oxygen, hydrogen. Now to divide your sugar into its constituent elements would be pretty difficult to do. It would require some pretty fancy chemistry. Okay, now eventually, suppose you were able to do that. We cannot divide these substances any farther. Hang on one sec. Sorry about that. So, where were we at? If we were able to divide the sucrose into its constituents, these can no longer be divided. They're the end of the line. These are elements, okay? We cannot separate them any further. And also water, once we break it down into its constituents, which is hydrogen and oxygen, we can't break those down any further, okay? So these are also elements. Elements cannot be broken down any further, even by chemical means. No fancy chemistry can you do that. Now, it's usually easy to separate a mixture. It's a little bit more difficult to divide up a compound into the elements. Okay, it's easy to break up a mixture into its components, but it's more difficult to break a compound up into its elements. Okay, now how would you divide up a mixture? All right, techniques for separating a mixture can be, well, you can melt something, you can heat it up until the solid converts to a liquid, and maybe that would help the components separate. Maybe you could boil something off and separate it that way. Maybe you can do sublimation. Maybe you can decant. You ever have like red wine that's got sediment in there and you want to pour out the wine, but you want to keep the sediment in there? You just slowly pour it out. It's called decanting. If you have mud water, you can pour it through a filter paper. That would trap the mud onto the paper, and the water would pass through. You can distill, So lots of techniques for separating a mixture. These are all examples of physical changes. Okay, physical changes are changes that only alter the state or appearance, but not the composition. During a physical change, no substances change their identity. Right? When you pour mud water through a filter paper, the entire time the mud stays mud and the water stays water. It's just they're being separated. No one's changing their identity. If you distill off alcohol from a water alcohol mixture, well, the alcohol is boiling off and the water is remaining behind, but the alcohol hasn't changed its identity and the water hasn't changed its identity. You're just separating the two. So no one changes their identity. That's a physical change. In chemical changes, on the other hand, these are also called chemical reactions. In chemical changes, atoms rearrange and new substances are formed from the original substances. So substances do change their identity here. That's what a chemical change is. You make something new. So how do you know if a chemical change or a chemical reaction has occurred? Suppose you're just watching something in a beaker. How do you know if a chemical reaction is actually happening or not? Because sometimes it's hard to tell. Well, sometimes it's just hard to tell. So some key indications is that if you see a color change, you know, like something is red, all of a sudden it's blue, right? Like if you're testing the pH of an acid or something, and it turns the litmus paper from blue to red. Okay, well, you have changed, you know, a chemical reaction has taken place on the surface of that litmus paper. Okay, substance has changed its identity. The litmus chemicals have changed their identity. If you see a color changing, if heat is produced where you don't even have a heat source, so if you have like two liquids in cups at room temperature, you pour one into the other, all of a sudden it gets hot. Okay, you produced heat from nothing. That's a good indication of a chemical reaction as well. Okay, heat is produced from the material itself. So chemical changes, you want to look for those two, maybe some other indications. Okay, you got it? Physical changes. No one changes their identity. Chemical changes, you do make something new. So examples of chemical and physical changes. Let's look at the textbook images. Let me get that ready. Oh yeah. Okay, so here's an example. Let's check this out. Everybody has seen dry ice, which is solid carbon dioxide. Okay, it's not water. Carbon dioxide, dry ice. Now, if you take a piece of dry ice and you set it out on the table, it will just evaporate. It doesn't turn into liquid. It just goes directly from the solid phase to the vapor phase. All right. Now, the formula for dry ice or carbon dioxide is CO2. So the stuff that you start with is solid CO2, and the stuff that you end up with after it vaporizes, that's still carbon dioxide up in the air, but now it's the vapor. It's gaseous CO2. And so this is how you would write the process right there. This is called a chemical equation. Okay, here is what you start with, solid CO2 or carbon dioxide, and this is what you end up with. Okay, gaseous CO2. But this is a physical change. No one's changed their identity here. You had CO2 to begin with, you have CO2 at the end. Okay, all you did was you changed the state. It's a solid and now it's a gas, but it's still CO2. Now, you can sort of, imagine the solid phase, all of these CO2 molecules, right? Each molecule contains one oxygen and one carbon in the middle, one carbon in the middle, and that's surrounded by two oxygens. So it's actually I'm looking for a molecule. So I have some over there actually, but you have the two oxygens on either side of the carbon in the middle. So the carbon in the middle surrounded by the two oxygens, and this time it's a linear molecule. Okay, so all of these molecules are packed together in the solid phase, but after it vaporizes, now they're all separated from one another in the vapor phase. Okay, if you were able to see the molecules, maybe that's what it would look like. How about sugar dissolving? So you take some sucrose sugar. The formula for sucrose sugar is more complicated. Each molecule of sugar is 12 carbons, 22 hydrogens, and 11 oxygens. So the way we write the chemical formula for a sugar is C12H22O11, and it's a solid if we're talking about solid table sugar. Now, when you dissolve that in water, now you have sugar water. It's still sugar, but to indicate that it's dissolved in an aqueous solution, you represent it as AQ in parentheses, aqueous. So you have solid sugar, and now you have aqueous sugar. But no one changed their identity. It's still sugar before and after. So this is, again, a physical change. Okay? So at the beginning, the solid sugar, all of these molecules are tightly packed together in the solid phase. If you were to pick up one little crystal of sugar, you know, that's what they would all look like if you could see them. Nicely ordered arrangement of the sugar molecules. And when you dissolve them in water, well, now the sugar molecules are separated from one another, and there are water molecules between them. Okay? You see the water molecules are between each of these larger sugar molecules. Now how about this? Propane gas. You take some propane and you burn it. That means you have your propane and it mixes with the oxygen, and when you make a spark, boom, it sets on fire, and you end up with something else. It actually turns into carbon dioxide and water. Okay, so you take your propane, the formula for, so here's your propane, it's you know, the gas, and the formula for propane is C3H8. Each molecule contains 3 carbons, 8 hydrogens. All right, now when you mix propane with air, which is the oxygen in the air, this is what you end up with. Okay, CO2, which is carbon dioxide, and H2O, which is water. All right, now this is a chemical change because, look, before you had propane, I don't see any propane afterwards. Okay, there's no propane anymore. It's disappeared. You've created something new. Okay, you've created carbon dioxide and water. You didn't have the carbon dioxide and water before, but now you do. So here's the chemical equation for the propane gas burning. You have propane, which is C3H8 gas. You combine that with oxygen gas. Okay, well, don't worry about this 5 here for now. We'll talk about balancing chemical equations later, but basically the propane gas and the oxygen gas form carbon dioxide gas and water gas. So this is what you have at the beginning, and that's what you have at the end. So substances changed their identity. You made something new, and that's a chemical change. When you make something new, that's a chemical change. All right? So, you got physical and chemical changes. What about physical and chemical properties? What's that? Well, a physical property is simply a property that the substance displays without any chemical changes needing to occur. So, it's something that you can observe without having to do any chemical reactions. For instance, if you have a substance, it can exhibit a certain odor, okay? Like, you know, propane gas has a certain odor, all right? It has that odor, and it doesn't have to do any chemistry for it to exhibit that odor. Another, you know, one is ammonia has an awful odor, okay? And it displays that awful odor without having to do any chemistry. Ammonia will stay ammonia, and it always smells. Okay? The color. You can look at the color of a substance and see what color it is without the substance having to change its identity, without it having to undergo any chemical reaction. So what color is it? In other words, if you're able to observe it without any chemical changes occurring, that's a physical property. Another one might be the melting temperature. Okay, for instance, water melts at 0 degrees Celsius. If you take a piece of ice and you warm it up and melt it into the liquid, it always does that at 0 degrees Celsius. Okay, no chemistry had to occur for you to observe that. The water was water the entire time it melted, before and after. Boiling. Okay, the boiling temperature of water is 100 degrees Celsius. You watch liquid water warm up, and once it reaches 100 degrees, it turns into gaseous water, but it's still water. Okay, the boiling temperature can be observed without any chemistry having to occur. The taste. What does it taste like? You can observe that. The density, how heavy is the substance? We can check the density without having to do any chemical reactions. So all of these are physical properties. Chemical properties, on the other hand, require chemical reactions. If you want to observe any chemical properties, that means you need to look at chemical reactions. In other words, is it corrosive? Is the substance corrosive? Well, if you want to check see if it's corrosive or not, you have to watch it corrode something. That's a chemical reaction. Okay, is it flammable? Flammability. If you want to see if it burns, you got to do a chemical reaction. You have to burn something with it. Okay, acidity is also requires chemical reaction. So chemical properties require chemical changes in order to observe them. So let's look at one more example of breaking down a mixture. So this time let's start with dirt water, a typical mixture you find in nature. This time this is a heterogeneous mixture. Okay, you remember the sugar water is homogeneous, evenly mixed all the way down to the smallest pieces. There are no clumps of sugar anywhere. All of those molecules are separated. Well, now we have dirt water, and we're saying this is heterogeneous. It actually, the composition does vary throughout. Now, you might have a lot of dirt at the bottom and a lot of water up here. And so you see the composition is different down here versus up there. And if you were to take a little teaspoon of dirt down here, it would look different than a teaspoon of the more liquidy stuff up there. Okay, now suppose you stir it up and you try to make it all even. Okay, and you say, is it homogeneous now? What if I stir it up? Does that mean it's homogeneous? It's all even throughout? Well, not really. Not according to a chemist, because I can take out a magnifying glass and I can see one of those dirt particles. Even if you can't see it with your naked eye, with a magnifying glass, I can see it. And if I can see it with a magnifying glass, that means on the molecular scale, there are billions and billions and billions of dirt particles to make up that tiny little dirt speck. That's a humongous clump of dirt on the atomic scale. Okay? And further, if I were to pour this dirt water into a filter paper, that tiny speck, would get trapped by the filter paper because, the mesh size of the filter paper is smaller than the speck. So the speck is huge. So anyway, if you can see it with the aid of a magnifying glass, that means it's not quite broken down into the atomic pieces. That's why dirt water is cloudy, because light cannot pass through. Those specks are actually pretty big. Now, if you want to separate this into the dirt and the water, that's easy to do. Again, you can pour it through a filter paper, and you collect the dirt over here and the water over there. So that's a physical change that we needed to do in order to separate this mixture. Now the dirt itself is still a mixture, and I don't know what that breaks down into. Probably lots of different things, depending on where your dirt comes from. Okay, so let's just forget about that. The water, we know that we can divide that into hydrogen and oxygen, and if we do that, we would get 11% hydrogen, 89% oxygen. That's because water was a compound. Okay, so again, breaking down a mixture, and the stuff that you end up with all the way at the end, those are the elements. All right, now the last topic in this chapter is energy. I think this is, not chapter, I'm sorry. I'm getting excited. We're not quite there yet. Okay, the first part of the chapter. Energy. What is energy? Okay. Anybody ever tell you got bad energy, dude? Bruh, you got bad energy. What are you talking about? You're not talking about the same kind of energy I'm talking about, okay? Energy in science actually has a well-defined meaning. It's not whatever you want it to be, all right? What energy actually is, here's a good definition. Energy is, it's anything that has the ability to push something else. Anything that has the ability to move something. That's energy. And we can measure it. How much can it move something else? It's usually defined as it's the ability to do work. Well, what work is the act of pushing something. So energy is anything with the ability to push something else. Anything that can do work, anything that can push something. So here, here's an example. You have a compressed spring with the ball attached right here. Now I would say that there is energy stored in this spring because this has the ability to push something. If that spring is released, it will push that ball. Now, I'm going to call this potential energy because it has the potential to move something else. It's not moving yet, but it has the potential to move something. If we release this spring, it's going to do that, and all of a sudden the ball is now flying. Now, there's no more energy in the spring, but there is now energy in the ball. The ball is in fact already in motion, so of course it has the ability to move something else or to push something else. Put anything else in its path. It would bump into it and it would move that object. So there's energy is now in the ball. Okay? And this time we're going to call it kinetic energy because now the ball is in motion. It's undergoing kinetics. So the energy was in the spring and now it's in the ball. And you could say that the energy was transferred from the spring to the ball. Okay? Energy is kind of like mass. If you lose 10 grams over here, you must gain 10 grams over there. You know, mass is never lost. It's always accounted for. Well, the same thing with energy. Energy is never lost. It's always accounted for. And if it leaves one object, it must appear somewhere else. Okay? Now you're wondering, how does it appear? You know, like, what is energy? Is it some kind of mysterious fluid? No. It's basically, motion. All right? Now, when you have a spring that's sitting there compressed, it looks like the spring is still. I don't see anything moving inside the spring. Well, the atoms and the molecules that are combined together have tension. They're kind of bent. And, you know, as soon as we let this go, you know, it kind of sends that ball flying. So, there's actually motion trapped in the bonds. You know, they're kind of the bonds that make up the material of the spring are compressed. Not very important to know the molecular interpretation of energy at this moment, but that's a great definition of energy. And if you were able to understand this, then you're doing really well. Energy is anything that can push something else, and whenever it leaves one object, it has to go to another object. And there is, just like the law of conservation of mass, which says mass is never created nor destroyed, there is a law of conservation of energy. Energy is never created nor destroyed. It just moves around. So the last part is I want to tell you about Mr. Reese's universe. Mr. Reese, someone I used to work with, highly respect. He likes to say, you know, I think maybe day one of his Gen Chem 1, is that the universe is made of matter plus energy. Okay? So the idea is that you look out there, the whole universe. If you were somehow able to put, to draw a boundary around it, suppose this is your universe right here. Okay? The universe. Now, the universe has a certain amount of matter in there. Okay? Here's a galaxy right here. There's a star over there. Maybe you have like a cat over here, right? So, you look around in the universe, there's a bunch of matter occupying different configuration, occupying different position, and that's the way it looks right now, okay? If you look at it 10 seconds later, it looks a little different. Okay, here's your universe a little bit later, right? Maybe that galaxy is still over here. Maybe that star has actually broken into two stars, and maybe that cat, wants to get away. Maybe it's over here now. So stuff has moved, right? But I guarantee you, if what these two laws are saying is if you count up all of the mass right now, it should equal all of the mass 10 seconds later. And if you count up all of the energy right now, it should equal all of the energy 10 seconds later. So basically, that's what the universe is. It's a bunch of matter that's stuck in there and a bunch of motion that's taking place. So the matter is moving around, and that's that. Now, we're not going to get into the whole, matter can turn into energy, right? Right, not right now. This is class in chemistry. You want to talk about how matter can turn into energy and energy can turn back into matter, right? Go take physics and talk a little bit more about that. And in physics, you'll talk about how matter and energy are really two sides of one coin, and instead of having these two laws, you have one law, the law of conservation of mass energy. So anyway, in the next video, we'll go into section 1.6. We're going to get into measurement and numbers. So, measurements, the units, the prefixes, milli, centi, micro, nano, all of that stuff. Powers of 10. We're going to do scientific notation, significant figures. We're going to do calculations and problem solving. All right, so I'll see you later.